confused for so long, it's not true.
Yes, here we are, dazed and confused. This is not how I like teaching physics. I hope that this little recording will be helpful for you. This is over what you've already looked at in your book on 7.1, and so I thought I'd just go over a few of the main ideas here within this little unit. There's also on your Google Classroom, there's a PDF of most of these slides, and so you can follow along there, or you can just watch, listen, learn. Just try not to fall asleep. No, no fun, no fun little toys and trinkets to play with, because this is some really cool stuff. By the way, that was a little Dazed and Confused by Led Zeppelin, and typically, if you were to walk into the room, I'd hand you some really cool sunglasses or some diffraction grading glasses, and we'd look around at some fun lights. But this is what we got to work with. So here we go. What you see here is some emission tubes, and if you look at them through diffraction grading glasses, they do something like this. They break up into these little spikes, and each element on the periodic table has its own signature light series. This was discovered by some friends of Mr. Bunsen. Yeah, Mr. Bunsen Burner. A couple of folks by the name of Kirchhoff and Fraunhofer. They were burning things like folks like to do, and they realized that every single element that they could find had its own signature light series. There was no model to predict why that happened, but it did lead to some other discoveries, like, oh, if you have a gas and it's cool and light comes through it, like from the stars, it absorbs those same spectrums that they saw. Like if this was per se, let's see this one right here. If it was helium, it would give off. If it was actually that's hydrogen, it would give off the same exact colors as it would absorb. And so you can look out into the night sky. If you have a white light from a star passing through a gas, that gas will only pull out the spectrum that it is the gas is made out of. And so that's how we know what gases are out in our universe. So let's bring it back to Earth. Maybe you've seen one of these before. If it was a different color like neon, it would be neon gas. Neon gas has its own light signature. This here is hydrogen. Hydrogen, of course, is the smallest, simplest little example that we can have. And we can only see 1, 2, 3, 4 light signatures from there at the specific wavelengths. These are wavelengths in nanometers. Nanometers. There we go. This one happened to be discovered, these 4 happened to be discovered by Mr., as it says right here, J.J. Balmer. There's other ones that we can't see. Lyman discovered some UV, and Paschen discovered some infrared, but we can only see Balmer's series. When you have seen a model of a hydrogen before, it probably looks something like this. It's one little electron down here, and it's got a proton in there, and it's really simple. Well, what happens here when hydrogen gets bombarded by maybe a light wave of a specific color, it gets that electron excited, and it's like, oh, it jumps up and boom, lands right there on another level, like the PS24, whatever chemistry stuff says, and it jumps up there, and when it's up there, it can itself go, this is up too high. I don't like being up this high at this energy level, and it gives off an energy. And notice the color change. This is red because that's a small jump, and if it jumps down from the third to the second, we can see it. Yeah, we see it red. It becomes de-excited. Now, this little picture that we see does not show you anything. This is like a Bohr diagram, and you might have put some electrons on the outer shell, but it doesn't show you the energy levels per se. But this one does. Here we have a way that physicists and chemists use to figure out how much energy is either absorbed or given off on a particular element. We only typically use hydrogen, like I said, because it's so easy. And here's our Balmer series that we can see. That's one electron. Just one electron. These are all of the jumps that it could do. Of course, it gets a lot more complicated when there are other other elements involved. But here it is, and check this out. If an electron was hanging out down here and enough energy hits it, it can go to infinity and beyond. And you know what we call those special little atoms? They're ions. Yeah, that's how an electron gets ionized, or an atom gets ionized. So it gets enough energy, and that electron gets knocked off. And we can put values to those energies. Here we see those values in electron volts. EV stands for electron volts. And there is a joules equivalent if you look on your data packet in that first, I think it's on the third page of all the known values, like the speed of light is on there. Well, this is something that you can go back and forth between joules and EV because it stands for the voltage of one electron, or electron volts. Units are your friends there. So let's take a look at some problems maybe that you could see, or some ideas here. Let's say we have, it says here, an electron jumps from N3 to 2. Whose do we call that? Whose is it? It's Balmer. Okay, well that's a pretty simple little question. But what happens if we want to find that atom's change in energy in EV and in joules? The first thing you note is that this chart is already given you the energy in electron volts. So there it is. And if you know how to do some subtraction, you can figure out how much electron volts of energy it gives off. So you can go 3.4 minus 1.51. Of course, we're going to end up with a scalar number because these are electrons, so they're negative. But do a little subtraction, you come up with, oh, it gave off 1.89 electron volts. And there's our conversion for going from electron volts to joules. So 1 electron, hey, remember that electron charge? 1.6 times 10 to the negative 19. Well, if you take that, multiply it by your electron volts, you get the joules, just like gravitational potential energy, kinetic energy, all that kind of good stuff. So there's our EV to joules conversion. Question, next one. Find in joules the energy of the emitted photon. Well, let's see. Well, we just did it. Let's see. What do we do back there? Oh, 3.02. Okay, there it is. Yep, it's right there. So if it's emitted from it, well, let's see. It could take it off. It could absorb it. That jump is always the same. Kind of like if you were to go up some stairs and if you went up to the next step, you increased your potential energy by that much, and if you went down to the step, you would be given off that much energy. So here's the energy that it gives away. Can't do half steps. If you've ever tried that, going up a set of stairs, it doesn't work out so well. You can only do, these are quantum ideas, like it's in a quantity that has to happen. Okay, so find the frequency of the photon that was emitted. Well, in the beginning of chapter 7.1, I have this little idea that E energy is equal to HF. H, of course, is again another number that can be found in your data packet. This is Planck's constant. Planck came up with the smallest unit that energy can be found in, 6.63 times 10 to the negative 34. You want to know where that number came from? Take HL physics. I'll explain it next year. But so here's Planck's constant, and if we go E equals HF, and we know what the energy is, there's our energy from the problem before, and we know what Planck's constant is because it's a constant, then we can do some gazintus, well actually those are divisions, and come up with the yes, that is the frequency of that light. There's our light frequency. And then of course, with V equals F lambda, back from good old waves, we could even find out the wavelength. So the velocity of light is still, this is light, it's still 3 times 10 to the 8th. If we know what the frequency is, we can even come up with the wavelength, which, if we went all the way back up to the top there, we could see those nanometers, and nanometers are in this range, so we know we must have a good number. We can move it over to nano because nano is -9, and so move that decimal point over 2 more, 1, 2, and that becomes 658 nanometers. So what's left on here is, hey, there's an answer. What's left on here is a few questions for you to do, and I put on Google Classroom a little quiz. This is the first time I've made a quiz like that in Google Classroom as well. I think I put an answer key on it, but I'm not sure if it'll work. We'll see how that works. But I'm just going to go silent here and I'm going to slowly scroll through the rest of my little PowerPoint. And if you really want to, you can check your answers there. So have a good time. I'll try to do a WebEx or a classroom discussion here. I'm going to try with my HL class first. And as usual, you can get a hold of me via email, or you can even put little comments in Google Classroom on this page particularly.
Won't a woman never bargain for you? Lots of people talking, few of them know. So